Welcome to a very short discussion on how numbers deceive. We're going to look at polygraphs, mammograms, and a couple other examples. So for instance, who played it better? Kevin had a higher shooting percentage both in the first half, 40% compared to 25%, and in the second half, 75% to 70%. Does this mean that Kevin had the better shooting percentage for the game? Well, you would think so, right? But you have to look at the overall numbers. So Kevin was 4 for 10, Kobe was 1 for 4, and then Kevin was 3 for 4, while Kobe was 7 for 10. When you add them all together, right, this is 4 plus 3, 7 out of 14, that's 50%. This is 7 plus 1 is 8. 8 out of 14 is better than 7 out of 14, so no, right? So the problem with breaking things into halves is they aren't necessarily equal halves. Okay, so this is an example of pretty much averaging averages, which you don't want to do ever. All right, so this is just describing what we've already talked about, the idea of 7/14 versus 8/14. Okay, test results. When a test comes back positive, that means you've tested positive for whatever they're testing for, right? So a positive test result just means that you have the characteristic they're testing for. So if you're doing, a test to check for high cholesterol, a positive result means you have high cholesterol, right? If you're taking a pregnancy test, a positive result means you are pregnant, right? If you're taking an HIV test, a positive result means you have tested for actually having the HIV virus. Okay, but again, tests can be inaccurate. So just because you get a positive result doesn't mean that it's a true positive. A true positive means that the test correctly reports a positive result. A false positive means the test comes back and says, yes, you have this characteristic, when in fact you don't, right? It comes back and says you're pregnant when you're not. It comes back and says you have HIV when you don't. It comes back and says you have high cholesterol when you don't. Those types of things. A true negative, just like a true positive, is when the test comes back negative and you in fact don't have that characteristic. And then a false negative is when the test comes back and says you don't have that characteristic and you do. The problem with tests is there are always, mistakes. No test is 100% sure, true and perfect. So based on the numbers in table 3.7, what is the percentage of women with negative test results who actually have cancer? These are what we would call false negatives. So this is a table of summary of results of 10,000 mammograms in which 100 of the women have malignant tumors and 9,900 have benign. If you don't know what that means, malignant means it's cancerous, benign means it is not. Okay, so keep that in mind. So if you were going to, a positive mammogram would mean that you have cancer. So that's why the true positive is in the intersection between a woman who got a positive mammogram and their tumor was malignant. But then there were this many positives where the tumor is benign. And that's because the mammogram is really just going to tell you that you have a tumor. It doesn't tell you whether or not it's cancerous. You have to then go on and have it biopsied and tested. So that's why there are so many false positives and also so many, true negatives, right? It's because you have to test further. So for the 10,000 cases, the mammograms are negative for 15 women with cancer and for 15 women with benign tumors. So the total number of negative results is those two numbers put together. Look back here and see 8430. That's the total number of negative results. So we want to know, what is the percentage of women with negative test results who actually have cancer? Well, out of all of these negative test results, how many actually have cancer? Well, 15. So remember, probability is just good over total. Good meaning it has the thing that we're asking for, i.e. has cancer. I know having cancer is never a good thing, right? Good just means has the characteristic we're looking for. So it'd be 15 over 8430. So we do 15 over 8430, and we can see 0.18%, right? So that's less than 1%. It's like almost 0.2%, right? It's less than 2 in 1,000. So in other words, the chance that a woman with a negative mammogram has cancer is very, very small. Suppose that 1,000 people take the polygraph test, 10 of whom lie, and the polygraph is 90% accurate. How many of those applicants who were accused of lying were actually telling the truth? So out of these 1,000 applicants, 10 of them lie, 990 tell the truth. The polygraph is 90% accurate. So out of these, it's only going to catch, right, 90%. So it's going to catch 9 liars, and 1 liar is going to get away. Out of these, right, it's 90% accurate. So we're going to take 90% of this, and 891 of them that are telling the truth is going to say are telling the truth. And unfortunately, 99 of them who are telling the truth, it's going to say lied. So it's going to accuse 108 people of lying, but 99 of these are falsely accused. And in fact, in reality, polygraphs are far less accurate than 90%. They're horrible. Okay, how about drug testing? It's another example of a test that can have problems with accuracy. All athletes participating in a regional high school track and field championship must provide a urine sample for a drug test. Those who test positive for drugs are eliminated from the meet and suspended from competition for the following year. Studies show that at the laboratory selected, the drug tests are 95% accurate and assume that 4% of the athletes actually use drugs. What fraction of the athletes who fail the test are falsely accused and therefore suspended without cause? You would think, 95%, only 5%, would be wrong, but it's all based on how many people actually, do the thing that the thing is testing for. So in this case, actually use drugs. So let's suppose there are 1,000 athletes in this meet, and we're told to assume that 4% of them, meaning 40 athletes, actually use drugs. And we would know this percentage just from, historical data type of thing. The remaining 960 athletes don't use drugs. So in that case, 95% accurate drug test should return the following results. 95% of the 40 athletes who use drugs, or 38% of them, would test positive, and the other 2 would basically get away with it. However, when you look at the 960 athletes who do not use drugs, right, 95% of them would accurately test negative, but 5% of them would test positive, and 5% of 960 is 48. So you would get 48 athletes kicked out for no reason. So the 48 false positives plus the 38 true positives tells you that there would be a total of 86 athletes who wouldn't be allowed to compete. And if you look at those numbers, 48 over that total of 86 represents 56. So 56% are actually non-users. So even though it says it's 95% accurate, out of all the people who had test results that said they were using drugs, more than 50% of those are false. So basically you're accusing innocent people. All right, let's look at one last example. Consider the 2 charts shown on the next slide. Both of these claim to show effects in 2011 of tax cuts originally enacted under President Bush in 2001. The chart in figure 3.5a, created by supporters of the tax cuts, indicates that the rich ended up paying more under the tax cuts than they would have otherwise. The other figure, created by opponents of the tax cuts, show that the rich received far more benefit from the tax cuts than lower income taxpayers. The 2 charts therefore seem contradictory, because the first seems to indicate that the rich paid more, while the second seems to indicate that they paid less. In fact, both of the graphs are accurate and show data from reputable sources. It's just the way in which they are reported that make each side seem to tell a different story. And that's one of the huge abuses of percentages. In truth, when you look at both of these, they both seem very confusing. So it would be much easier if they could just give you some numbers and so you could figure it out yourself. But there you go. There's the last example for this one.